It's, it's great to see so many familiar eyebrows in the audience. And, you know, this was originally OPAC 2020, and I see that in the extra 2 years of advertising space, we've gotten the word out very well. So my name is Ben Brubaker. I'm the department head at the University of Minnesota and an enthusiast of algebraic combinatorics. So I'm giving the opener on behalf of my co-organizers, Vic Reiner, Greg Musiker, Pasha Piliowski, and Christine Burkesh on Zoom. So thanks to all of them for their efforts. I have a few simple basic announcements, and then I'm going to turn it over to Pasha, who's going to chair the morning session. First of all, restrooms are located out this door and up on the first floor as well. Throughout this conference, we're going to have talks primarily situated in this room, but we also have use of Vincent Hall. If those of you who have visited us before know that Vincent Hall is the home to the School of Mathematics and it's just straight across the quad. So during the breaks, you can hang out here for coffee, or you can be outside in the 70-degree weather of Minnesota this week, or you can cross the quad to Vincent Hall and spend time there in the collaboration spaces, particularly on the first floor. We have a lounge with coffee there, and we encourage you to spread out and use those spaces. Vic assures me that he has placed Hagoromo chalk in the collaboration spaces along the first floor. So we expect major research to be done as a result. In terms of dining options, the dining is mostly limited to the commercial areas which are around the university. We've built in 2 hours between when the morning talk ends and the afternoon talk begins, so that should be plenty of time. If you want recommendations for where to dine, ask any person with a University of Minnesota affiliation, and we will be happy to direct you to a good place to eat. We're all friendly. Okay, in terms of questions, you can ask questions the old-fashioned way. You can raise your hand. Also, if you're on Zoom, Trevor will be moderating this morning's chat session, and if the speakers could occasionally ask for questions, that would be a great help. We'll take them off of Zoom in those intervals. If you have other questions, you can ask any organizer. And this is also a great time to thank our dedicated staff for all of their work in putting this event together. I want to thank particularly you've met Catherine Dowd and Georgia Kroll, who've been manning this event and providing lots of support to us. Pasha, I turn it over to you to introduce our first speaker and talk about the conference.
Okay, hi everybody. It's really nice to have you here. We are very happy you all came. And I'll just say a few words about, well, the idea of the conference is just what it is. We thought it would be good to have such conference. And so the conference is structured so that to fit best this idea. So, right, so there are 30-minute breaks between any talks to give people enough time. So for example, speakers don't have to talk 50 minutes. They can talk 60 minutes. They can talk longer if they want. So usually, also, so once the talk is over, right? So there's a talk, then we ask questions at the end of the talk. But the idea of giving the 30-minute break was to give people time for discussion with the speaker and with each other about what they just heard. So at this point, people are very much welcome to come to the speaker to the front and have a discussion here, or catch a speaker in the coffee room in Vincent Hall afterwards. And the first 5 minutes, kind of, we want to especially encourage sort of young people like graduate students, postdocs to come to the speaker and ask any questions they have, because usually young people are shy. So the first 5 minutes after the talk is over, you know, we send everybody off. Nobody's leaving because everybody wants to talk to speaker. So please give young people opportunity to ask questions. Okay, that's it. So now let's start with our first speaker. We are very pleased to have Sergey Fomin, who will be our first speaker. And he will talk about Quiver mutations.
Test. Can you hear me in the back? Okay. I'm very happy to be here, to be at this, what promises to be wonderful conference. It's been a while since we attended conferences in person, especially in such large numbers. So I think everybody here is excited to finally meet with friends and discuss their research projects and maybe also come to some talks and enjoy them. I will be focusing my presentation on people who are in the room. My apologies to those who are on Zoom. I won't be addressing you directly. And I will be pointing my pointer to the left screen. So don't look at the right screen, that one. Look at this screen. All right, and once again, thanks to the organizers, and let's begin. So this talk is about quiver mutations. So these are, this is the combinatorial underpinning of the theory of cluster algebras. I won't be talking about cluster algebras today at all. So if you don't know the definition, that's perfectly all right. You just need to believe that this combinatorial notion is important for something, something important, right? What are these? So let me give you a definition carefully and precisely, because everything else will be very kind of bird's eye view, and I won't be, of course, proving anything or explaining much of what's going on, but I will just state open problems as I was encouraged to. So a quiver is just a finite oriented graph. People in that part of the world didn't know graph theory, the standard terminology, so they invented it, this term. To be clear, we allow multiple edges. We don't allow loops, that is edges which are, whose endpoints are the same, or arrows as they are called in this part of the world. And we also don't allow oriented cycles of length 2, meaning if two arrows go, connect the same pair of vertices, but in the opposite direction, then they just annihilate each other. So here is an example of a quiver. And also some of you may be familiar with a more general setup where some of the vertices of a quiver are declared frozen. So we won't be considering this setup here today. So if you don't know about this, you're in good shape. So quivers are essentially cryptomorphic to skew-symmetric integer matrices. So instead of thinking about quivers as I define them, you can just think about skew-symmetric integer matrices. Zeros on the diagonal means that we are not allowing loops. And of course, all that matters is how many arrows you have from, let's say, in this case, vertex number 2 to vertex number 1. Well, there are two arrows. Here they are. And in the opposite direction, well, nothing, but we put -2 to signify that the arrows go in the opposite direction, right? So hopefully the correspondence is clear. So we can recover a quiver from such a matrix, and a quiver determines such a matrix. There is a more general theory which, instead of dealing with skew-symmetric matrices, deals with skew-symmetrizable matrices. And this is kind of parallel to the case of Cartan matrices, where you can consider simple lathe cases, ADE, or you consider skew-symmetrizable, symmetrizable Cartan matrices. In finite type, they would be, B, C, F, and G. So you can imagine what a skew-symmetrizable matrix is, and you will be able to imagine what the analogs of various open problems that I will be stating are in that generality. But today we won't be talking about that generality. So I just want to keep everything as simple as possible. All right, so the key definition is one of quiver mutation. So this is a transformation of a quiver, equivalently of a skew-symmetric integer matrix, which is computed in 3 steps. Okay, so, well, maybe step 0 is that we pick one of the vertices of the quiver. In this example, vertex Z. Okay, and there are apps online, or you can download a standalone version. So you see the quiver on the screen, and you drag your mouse to that vertex, and you click on it. And then something happens to the quiver. It gets transformed. Okay, so if you're not interested in the definition, that's all that you need to know. But if you want to solve some of these problems, you would like to know like what's the rule of this transformation. Okay, so the first step is that for each instance of a 2-arrow path passing through Z, only through that special vertex Z that we are clicking on, for each instance of transitivity like this, we introduce an extra edge from X to Y, kind of the product of those two. Okay? So in particular, if we had, let's say, 2 arrows coming in and then 1 arrow coming out, and we are clicking on this vertex, then there will be 2 extra arrows introduced, right? So if you had K arrows coming in from X to Z, and then L arrows going from Z to Y, then you will have to add K times L arrows from X to Y, because for each pair, an arrow like this and an arrow like that, you will need to add a new arrow. Okay? So that's the first step. For example, you can see here that we had here, let's say, well, this one and this one, right? And I clicked on Z, so I added this second arrow, and here you see that second arrow. Now we have 2 arrows. All right. Then we reverse the direction of all arrows incident to Z. So these 3 arrows in this picture get reversed. Okay, after you did step 1, you do this step 2. And finally, we do the cancellations. If we have a pair of arrows that point against each other, they annihilate each other, and if needed, we repeat it. So for example, here we had arrow coming in and then out. By transitivity, this would add another arrow from here to here, but we already have an arrow pointing in the other direction, so those 2 arrows get canceled out, and we just get nothing. Okay, hopefully you see how applying this definition to this example gives you the second quiver from the first one. Of course, the main question that should be on your mind, why this definition? Like why should we care? I mean, this entire talk will be discussed to this, will be devoted to the discussion of this definition. So why should anybody care about this? And the answer is that this has to do with cluster algebras. And this is the definition which makes everything click, like the Laurent phenomenon and various other properties. Another kind of explanation is that surprisingly many types of combinatorial transformations can be described as an instance of this, like braid transformations of configurations of pseudolines, for example, and various like local moves in various skein theories and so forth. So flips and triangulations. There are many instances where we do something to a combinatorial gadget, do some local transformation, and you can interpret this as a quiver mutation by translating it into the language of quivers. Quivers of some special kind, to be sure. The first observation is that this is an involution. If you click again on the same vertex, you recover the original quiver. This is easy to check. I won't be bothering you with formal proof. Okay, so the next definition is that of mutation equivalence. We say that two quivers are mutation equivalent if you can transform one into the other by a sequence of these clicks. Of course, up to isomorphism, everything, because we have, you know, two distinct quivers. Each of them has its own set of vertices. So. And this will be our notation just for this equivalence relation. So exercise, if you don't want to listen to me from now on, just want to occupy yourself with something, take any two of these quivers and check that they are mutation equivalent. So I claim that you can get from this one to this one, from this one to this one, of course, from this one to that one, by a sequence of mutations. We denote by bracket Q the mutation equivalence class of a quiver. So these classes for two quivers are the same if and only if they are equivalent. And we say that the quiver has finite mutation type if this equivalence class is finite. So you click and click and click. So if you started with just a random skew-symmetric matrix or a random quiver, random in the sense that like lots of arrows between each pair and how many just you decide at will, then almost surely you will never get the same quiver more than once. That is, you can mutate away and you will get a whole tree of possibilities, and all vertices of that tree will be distinct, meaning all the quivers will be pairwise non-isomorphic. So it's rare that you get even two, you know, isomorphic quiver, let alone the whole tree collapsing to just a finite set of quivers. So this is a very, very special situation. Oh, so this is the tree that I just mentioned. So you start with a quiver, then you can mutate. Let's say your quiver has three vertices. You can do mutation mu1 or mu2 or mu3. And then again, you can repeat. If we repeat the same mutation, then we just go back in the tree. So that's why it looks this way. And once you have this mutation class, then you can define a cluster algebra. So a cluster algebra, whatever that is determined by the mutation class, not by an individual quiver. Okay? So you define certain birational transformations that are associated to these edges of this graph, and then you take certain elements that these things generate inside some field of rational functions, take the ring they generate. Anyway, those of you who know the story will recall it. Those who don't, never mind, because I will just be talking about combinatorics today. But of course, cluster algebras are in the back of my mind, and maybe they will be in the back of your minds too. So the first problem, which is really the main problem today, I mean, for me, it's the main problem, is that we don't know how to determine whether two quivers are mutation equivalent. Okay? And by we don't know, I don't mean that we don't know a good way or an efficient way. We just don't know any way. We don't have any algorithm that would detect whether two quivers are mutation equivalent or not. So if I give you two quivers, say on 100 vertices, of course you can say, okay, why cannot I just exhaustively mutate in all possible directions? Well, how do you know how far you need to mutate? So let alone that it will take you 100 to the nth time to examine all the possibilities and mutations away, but you don't even know like when to stop, how big n should be. Of course, it would be absurd if this were algorithmically undecidable. There must be an algorithm. Well, who knows, right? Maybe you can encode using this problem, some other problem which is known to be algorithmically undecidable. Okay, maybe, but I expect such an algorithm to exist. I just have no idea how to construct it. Just literally no idea. So this is not just an open problem, it's like a very wide open problem. No, we don't even know where to start. For n equals 3, we know how to do it because there exists like an infinite descent process. So for each quiver on 3 vertices, there is a mutation that brings some kind of semi-invariant down, and it's a unique one. So there is a distinguished direction in which you need to mutate if you want to make your quiver smaller, and you keep going in that direction until you are at a minimum, and that will be a canonical representative in a given mutation class. And then you compare those 2 representatives for 2 given classes, and you're done. And this approach does not work already for 4 vertex quivers, by which I mean there doesn't exist a proof like this. And it doesn't exist because, as I will show you at the last slide, there exist very, very long cycles of mutations that can bring you back to the same quiver. And this tells you that essentially this type of argument is doomed. Yes?
So I'm trying to understand what it means this can't work. So what kind of statistics do you know can't be made to get you to set it down?
No statistic can work because there exist these very long mutation cycles. And so there is no distinguished direction in which you need to go. Like if you take a point where there is that your statistic is maximized along such a cycle, you don't know which direction to go, because both directions will bring you to the minimum, and therefore like there is no unique way of going. I mean, of course, if you use something like the diamond lemma or something, I mean, but then how do you prove it when your cycle is like 100 steps long? I mean, I don't know if I explained it, if I answered your question or not. I mean, there could be some more sophisticated arguments of this sort, but there literally doesn't exist a statistic on quivers which has a unique descent at each quiver.
Oh, okay, thanks.
Yeah. All right. Somehow my clicker doesn't work. Oh, okay. So there is a class of quivers that come from so-called Playbig graphs. These are planar bicolored graphs coined by Postnikov, this term Playbig. And you can see from the picture how the quiver, which is shown in red, is determined by a graph. Basically, the arrow of the quiver cuts across every bicolored edge. So if it's same colors, then there is no such thing. And then the direction is determined so that the black is on your right as you move in the given direction. So the observation already made by Postnikov is that local moves translate into quiver mutations. So for these quivers, not every local move will give you a mutation. Sometimes the quiver will not change. More importantly, some quiver mutations will not, even for quivers like this, will not come from local moves. But there is a conjecture made by Michael Shapira that basically tells you that within this class of quivers, Postnikov moves determine mutation equivalence. So you don't need to, if I give you two Playbig graphs and the quivers that come from them, in order to decide whether they are mutation equivalent or not, you can stay within the land of Playbig graphs. And so, assuming this is true, a natural problem arises: determine whether two given Playbig graphs are move equivalent. I don't know how to solve this problem, but there has been some partial progress. In particular, already Postnikov solved this for reduced Playbig graphs. But yeah, I won't be telling you what that means, but in general, I don't know how to do this. And then there have been some other progress. On the next slide, I will explain what it was. So a partial progress towards detecting whether two quivers are mutation equivalent or not is to introduce some invariants that don't change under quiver mutations. And so then, in some cases at least, we will be able to say that two quivers are not mutation equivalent because those invariants take distinct values at those quivers. Of course, the number of vertices in a quiver doesn't change. That's easy. Less obvious is that if you take the rank or the determinant of that skew-symmetric matrix, these two things don't change. Of course, if your quiver has an even number of vertices, then the determinant doesn't change much, because the determinant of a skew-symmetric matrix of, even or odd? Odd, yeah, of odd size is 0. But if the number of vertices is even, then, you know, it's even the square of a Pfaffian, so the Pfaffian up to sign doesn't change under quiver mutations. Also, the GCD of matrix entries in each column or row of your matrix is an invariant. That's basically it as far as combinatorics goes. Now, there are some more sophisticated invariants, like you can use the work of Thomas Lamb and David Spire on cohomology of cluster varieties to construct some very, very complicated, difficult to compute invariants, because they are, invariants of the cluster variety, which is, the spectrum of the cluster algebra, which, as I told you, only depends on the mutation equivalence class. But it seems strange that you have to go through such convoluted constructions, very complicated, in order to distinguish just two oriented graphs from each other. In the case of Playbig graphs, there is a construction of a link associated with a Playbig graph, or more precisely, transverse link. So this was done in my work with Pasha Pulevsky, Zhenya Shustin, and Dylan Thurston. And that link doesn't change under Postnikov moves. So modulo Shapira's conjecture, basically, this solves the problem of mutation equivalence for Playbig graphs if this invariant is complete. But of course, there is no reason to expect it to be complete, right? And so the next problem that I suggest is find new invariants of quiver mutation. Yes? Yes, I looked at Smith normal. Yes, it didn't doesn't really help much. Yes, but you're right. So we can look at just what is known about invariants of like skew-symmetric quadratic forms over Z, and people studied that, and it doesn't really help much. Like even for 3 vertex quivers, it almost doesn't do. I mean, you can have basically you can have quadratic forms equivalent under some transformations over Z, but not under the ones which come from mutations. And I have no idea how to distinguish, which ones are those. Okay. Here is a very specific example, just to show you how little we know. Let's take 2 grid quivers. So grid quiver has this pattern of vertices, and the orientations are such that every little square is oriented. Okay, either clockwise or counterclockwise. By the way, this whole construction, this whole entire business is equivariant under global reversal of arrows. So you take a quiver and reverse all its arrows and then do a mutation. It's the same as first do a mutation and then reverse. So you can think about each quiver like together with its antipode. And yeah. All right, so let's take 2 quivers, which are grid quivers, and chosen so that the number of vertices at least is the same, 12 in this case. Otherwise, of course, it's easy to say that they're not mutation equivalent. So how to show that they're not mutation equivalent to each other? Maybe by using David and Thomas' technique, one could do it, but it's not clear to me how to do it. So even there is not even a simple way to show that 2 quivers like this are not mutation. I will talk, excellent question, and I will touch on it later on. Right, so if they are non-isomorphic, then which invariant distinguishes between them? A quiver is called acyclic, well, if it's an acyclic directed graph. And Calderon and Keller proved 16 years ago that acyclic quivers are mutation equivalent if and only if they are related via sink source mutation. So a sink or source, if you mutated a sink or a source vertex, then there are no transitivity situations. So all that happens is that all the arrows at that vertex get reversed, and that's it. Nothing else happens. So, and this keeps your graph acyclic, so your quiver. So this is one way to get from one acyclic quiver to another. And that's the only way by this theorem. So you cannot start with an acyclic quiver and do something complicated and then obtain another acyclic quiver. In particular, addressing the question that you asked, orientations of non-isomorphic trees are not mutation equivalent. And we don't know an elementary proof, even of this corollary, let alone the theory of Calderon and Keller. So that one is used using additive categorification, like triangulated categories, that sort of homological algebra machinery. And so there is no elementary proof known of this theorem or even of this corollary. Elementary meaning a proof that does not require categorification. We call a property of quivers hereditary if it descends to an induced subquiver. So in this theory, they call it full subquiver, but this is really just an induced oriented subgraph. So you take a subset of vertices and all the arrows between them, and throw away everything else. And so if a property descends to any such subquiver, we call it hereditary. It is inherited from the bigger one. And examples include, for instance, quivers of finite mutation type. It's easy to see because, you know, if you only get finitely many quivers in the big one, when you mutate in the small one, then you also, oh, I didn't tell you, but when you mutate within a small subquiver, the subquiver itself mutates as if there was nothing outside it. So, of course, those mutations also affect stuff happening outside, but there is also a notion of quivers of finite type, which I won't define, but they are in particular the ones which can be mutated to an AD Lincoln diagram, an orientation of that. We call a quiver mutation acyclic if it can be mutated to an acyclic quiver. Here is another theorem that was proved using categorification techniques by Bohan, Marsh, and Rayton, that this property is hereditary. So if you have a quiver which can be mutated to an acyclic quiver, and then you take a subquiver of that quiver, then it also can be mutated to an acyclic quiver. So this is a highly non-trivial result and combinatorially very unintuitive. So your quiver itself will have lots and lots of cycles. It just can be mutated to something that doesn't have cycles. And what I'm saying is that once you restrict to a smaller one, then the smaller one can also be mutated to something that doesn't have cycles, even though the sequence that mutates the bigger one to an acyclic quiver will involve mutating all over the place, including outside that subquiver. So you cannot just restrict that sequence of mutations. And again, no elementary proof of this result is known. Not for the lack of trying. And as you can see, it's been a while since those theorems have been proved, and we still don't have elementary proofs. We say that one quiver is embeddable into another, or sometimes that the first mutation class is embeddable into the other, if the first quiver can be embedded as a subquiver into something which is mutation equivalent to the second one. We can also say this is equivalent to also allowing to mutate the first quiver and then embedding. So it's more natural to talk about embeddability of mutation classes. So one mutation class made of smaller quivers is embeddable into a bigger one if any quiver in the small one is a subquiver of somebody in the bigger class. This, of course, gives a partial order on mutation classes. Just to illustrate that this is not a crazy concept, a quiver is of infinite type, means it cannot be mutated to a Dinkin diagram if and only if some two-vertex quiver with at least two arrows is embeddable into your quiver. Okay. In other words, you are given a quiver and you try hard to mutate it into something which has multiple arrows. If you can do it, then your quiver is not of finite type. If you cannot do it, then it is. Of course, how do you figure that out is another question, but suppose you can. And if you want to get at least 3 parallel arrows, you can do it if and only if your quiver is of infinite mutation type. And of course, getting at least 3 arrows in the same direction is the same as embedding a 2-vertex quiver with that many arrows. This was proved by Felixson, Shapiro, and Tumarkin. So the natural problem is how to detect whether one quiver can be embedded into another. This is even more hopeful, hopeless. This is even less. Sorry. It's even wider open than the mutation equivalence problem, because of course, in order for 2 quivers to be mutation equivalent, you know, if they are of the same size, then it's the same as just being embeddable, because the number of vertices is the same, then embeddable just means mutation equivalent. In fact, we don't know how to do it basically for any small quiver, as long as it has at least 2 vertices. Of course, 1 vertex is embeddable into anywhere, but once you have 2 vertices with any number of arrows, 0, 1, 2, 3, and so forth, we don't know how to detect embeddability. We know how to detect that you can embed something with at least so many vertices. I showed you a couple of examples, but not exactly. In other words, let's say I give you a quiver and I ask you to mutate it so that there will be 2 vertices with no arrows between them. I have no idea how to decide whether this is possible or not. Of course, this seems like a silly question to ask. I agree. It is a silly question, but it just illustrates. So don't spend too much time on this one. But it just goes to showing how little we understand about this business. Here is something that maybe can be understood. Let's take trees again. Experiments show that perhaps one tree is embeddable into another if and only if the bigger tree can be contracted to the smaller one. Okay, by just repeated contraction of edge. When I say tree, I mean a tree with some orientation of its arrows, and it's easy to see that all orientations of a given tree are mutation equivalent to each other, just via sinc source mutation. So this is, so choosing orientation is immaterial. Okay. Here is another brain teaser, hopeless one, maybe. Well, who knows? The following result was obtained by Greg Muller. This is the Markov quiver on the picture. It is very special because no matter how you mutate, you get an isomorphic quiver. So this quiver is kind of a fixed point for the mutation business, because when you mutate here, you get 2 arrows and 2 arrows. So you will have to add 4 arrows, right? 2 times 2 is 4. 4 arrows going from here to here. Oh, sorry, I should be pointing at this screen. 4 arrows, right? And but 2 arrows as a result going into this direction. And of course, these arrows will get reversed because we are mutating upstairs. So as a result, all 6 arrows will get reversed, which is the antipodal quiver, which is isomorphic to the original one. Yes, Jim? Why it's called Markov? Because the corresponding cluster mutations give you the Markov numbers. So this is the process that is described in particular in your survey, but many other places. Right. I mean, it's a great, I highly recommend it as an introduction to the subject. More is true. You cannot embed the Markov quiver into the quiver of any reduced Playbig graph. I didn't tell you what reduced means, but many of you know. In particular, the grid quivers, for example, are such. This follows from a theorem of Greg's about the existence of a reddening sequence being a hereditary property. I didn't define what this means, but anyway, it's some property which can be combinatorially defined, and it is mutation invariant and hereditary. And the Markov quiver just follows from the invariants. It has no reddening sequences. And then there is another deep result by Nick Ford and Kristina Sergeyenko that the quiver of any reduced Playbig graph does have a reddening sequence. So if you could embed the Markov quiver into such quiver of a reduced Playbig graph, then by Ford-Sergeyenko, it would have to have a reddening sequence, but it doesn't. With Kiyoshi Igusa and Kyung-Yong Lee, we proved, on the other hand, that any quiver can be embedded into the quiver of some Playbig graph, possibly non-reduced. So this is showing that if you take quivers of all Playbig graphs and then everything which can be embedded into them, like, so take arbitrary quiver of a Playbig graph and then restrict, then up to mutation, you can get any quiver at all. Whereas if you start with reduced Playbig graphs and play the same game, then you won't get any quiver. You will necessarily only get quivers which have reddening sequences. So this tells us that arbitrary Playbig graphs are much wilder than reduced ones. Okay, and to finish, let me talk about mutation cycles. So a mutation cycle is a sequence of mutations where, of course, we don't repeat the same mutation twice because that would just annihilate. Those two mutations would cancel each other. So you do mutations, and somehow by magic, you return back to the same quiver that you started with. Well, an isomorphic one. So that we call that a mutation cycle. Why is that interesting? Because this typically leads to interesting integrable dynamical systems. So if a sequence of mutations brings you back to the same quiver, this means that you can repeat it again and again and again. And you can do the same with the associated cluster transformations, whatever they are, right? So you get a sequence of maps that you can iterate. And there is a general belief that any such map will be completely integrable, basically because the Laurent phenomenon will force algebraic entropy to be what it is. There will be massive cancellations in the rational functions that you will get because in order to ensure monomial denominators, and those massive cancellations are kind of a signature mark of integrability. So it's interesting to study situations where a sequence of mutations brings you back to the original quiver. And there are many examples. For instance, if you have two vertices that are connected by a single arrow, not multiple arrows, just one. And if you mutate at those two vertices in alternation 5 times, exactly 5 times, then you get a quiver which is isomorphic to the original one. This is non-obvious if you just learned what a quiver mutation is, but it's true. It comes from cluster algebras of type A2. So the pentagon identity of some sort. Additional examples come from, for example, for more general quivers of finite mutation type, like the ones which are associated with triangulated surfaces, where each then twist, or more generally, like element of the mapping class group, will be associated to some kind of sequence of mutations that gets you from a triangulation to the twisted one. Homologic periodicity is another example. Of course, here we don't just have integrability, but we have integrability or even linearizability. And of course, there are papers by Pasha and Pasha that I highly recommend on this topic. And then there are mutation periodic quivers of Fordy and Marsh. Sorry, you cannot see. Yeah, I don't know how to. Okay, you can see Fordy and Marsh in 2009. But these are all of these are very special examples. So one natural question to ask is, can you build very long mutation cycles, or they're basically all pretty short? Once you know how many vertices you have, then you can do something, but not much. I mean, like if you have only 4 vertices, let's say, then any mutation cycle has length at most, I don't know, 1 million. Well, 1,000 probably, even 100. So in all examples above, the length of any such mutation cycle, of course, we don't repeat the same cycle over and over again. So let's just demand that once you come to the same quiver again, you stop. The length is bounded from above by a function of n, the number of vertices. Surprisingly, as Scott Neville and myself established, for any n, which is at least 4, there exists of mutation cycles of arbitrary length, which don't, all of whose quivers are distinct. So you can find a quiver on 4 vertices, and then a mutation sequence of 1 million mutations that gives you back the original quiver, and all the intermediate quivers will be distinct pairwise. So this shows that we really understand very little about what can happen and what not, because the intuition coming from the n = 3 example is that if you just put some crazy multiplicities, then you will just get a tree of possibilities and everything will be distinct. Of course, maybe the reason those cycles are so long, you might speculate, is that they can be paved by short cycles. Like in the cluster business, there is this brick wall example of a fine type A2, where you can get a very, very long cycle in the exchange graph, but it is paved by pentagons. Of course, that's exchange graph, not the graph of quivers, but still, like, it's not surprising that you can get something like that. So from that point of view, it's the more reasonable question is which primitive mutation cycles exist. So cycles which cannot be paved by shorter cycles. By paved, I mean that they're not like, if you draw, you cannot draw a commutative diagram of mutations where, you know, there will be these little cycles and then on the outside you will have a big one. But it turns out, as we established, that already for quivers on 4 vertices, there exist arbitrarily long primitive mutation cycles. Not just arbitrarily long cycles, but cycles which cannot be paved by shorter ones. And moreover, the quivers that appear in those cycles are generic in the sense that the multiplicities, they don't satisfy any algebraic equation. Like, you know, Zariski closure would be everything. So the weights, the entries of the exchange matrix, they only need to satisfy certain very, very complicated inequalities, but not equations. And then you can manufacture a cycle of length 1 million just for 4 vertex cycles. And that's my, okay, before I finish, right? Because you are not a graduate student, I gather. So go ahead and ask your question, because once I finish, only they will be allowed. Go ahead.
This sounds like, I don't know I haven't read the result, of course, but it sounds like something very special for 4 vertices. I mean, are there examples with 5? With similar?
Yes, we are. In fact, I was checking the proof yesterday, and I was thinking of putting in the statement for quivers on n greater than or equal than 4 vertices. We have a construction, we have a proof, but I just wanted to be totally sure because, you know, I'm being recorded and this will be, so I don't want to risk my reputation. But yeah, this is not special for 4 vertices. Yeah. Excellent question. And that's it. Thank you very much to everybody.
Okay, we have time for a couple general questions, and then we'll maybe see if anyone on Zoom has one as well. Sergey, do you want to just call on anybody that has a general question?
Yes, please.
Are all of the cycles of bounded length, or maybe arbitrarily long within one class?
Okay, so the question is, for a given mutation class, can the cycles be arbitrarily long? You mean primitive, probably?
Yeah.
Right. Actually, I don't know. Scott, do you think it's true? Huh?
For 4, it's definitely finite.
Finite, yes. So yeah, my expectation is that probably it is bounded for a given mutation class, right? Yeah, interesting question. I mean, great question. We didn't think of this. It's but it's very natural to ask. Okay, great. Other questions of? Are you a graduate student? I was told.
So you can take general questions, and then we'll clap one more time, and then we'll invite the graduate students down.
Oh, I see. Oh, all right. Yes, there is an app. So if you go, there are several apps actually for Quiver mutation. If you go to the Cluster Algebras portal, which I maintain, so there is a link for my homepage, but also you can just Google Cluster Algebras portal. There is a category there, software and data, and there are links to several pieces of software. There is a Sage package that Greg and Christian Stu, I think, and some other people developed. There is an applet in Java by Bernhard Keller. You can either use it online, running on their server, or you can download a standalone version. For Playbig graphs, Pasha Galashin wrote software. There must be more that I don't remember. So that's very useful. It really comes in handy in sort of developing intuition for what we are doing. So I spent many hours, I must confess, this is addictive. I don't play any computer games or video games or anything like that. But so this is my vice. I can spend hours, mutating quivers and just to develop intuition, like what can happen and what cannot. Yes.
So you had on slide 5 3 sets.
Yes.
One of them is this nice triangle.
Yes.
We take bigger versions of that triangle. What's the triangle?
Right. So the question is was about this. No. Yeah, this slide. So here, these are 3 quivers of type E6, because this is an orientation of Dynkin diagram E6. And Alan's question is this particular quiver kind of representative of something, right? Geometrically, right? And the answer is yes, that this is, so you can imagine drawing like a triangular grid, a bigger one, and orienting it accordingly. And that corresponds to the cluster structure on several famous varieties, or more precisely their invariant, their coordinate rings. So it's either the basic affine space, which is like GIT quotient G mod U, or you can take U is the unipotent radical of a semi-simple Lie group, or just directly on U, U, capital U, and or what else? Well, you need to take flags and then take like multi-cone over that to make it an affine variety. But also, this is a general phenomenon that this can actually be mutated to some kind of grid, at least for maybe even or odd values of the parameter. So there is also some kind of Grassmannian sometimes that has the same cluster structure. Chris Fraser has a paper that establishes that quasi-isomorphism between those things, right? But basically, the main example closest to my heart is the basic affine space, because that's this G mod U, because that's a space where all irreducible modules, for GLN are contained, each with multiplicity 1. The classical construction of Frobenius. Yes.
Is there any hope of turning the non-elementary
Okay, so the question is there a hope for turning one of the non-elementary proofs into an elementary one just by unpacking it and somehow making it elementary? I doubt it, honestly. I cannot really pinpoint, like, because this relies on this result, which depends on axiom of choice or something. you know, I'm very skeptical. I think people tried, but I cannot guarantee it.
Okay, let's thank the speaker again for a lovely talk. Sergey really embraced the spirit of this conference with open problems galore, and even introduced his own classification with open, very open, and wide open problems. So that's fantastic. So now we'll invite everybody to take a break. Our next talk will be virtual. 85% of the talks will be in person for this conference, but the next one happens to be virtual. We will broadcast it here and sit in a very 21st century way in front of our speaker, who will be Joel Kamnitzer. But you're also welcome to watch it on Zoom via your laptop from anywhere around the building. Okay, so graduate students, you're invited to come down if you have further questions, and everybody else enjoy the break.